All right, in 9.6, we're going to look at the ratio and root tests for series convergence. Now, these are going to be two sort of unique tests in that they're going to allow us to find the convergence of an infinite series, but they're going to work on a three sort of pronged outcome. All right. So these tests are really good for special types of series. Specifically, series that we haven't necessarily dealt with before. So series that are not alternating, series that aren't easy to integrate, or series that aren't easy to compare. So obviously, when we have easy to compare to other things we know, we've dealt with the comparison test. When we know how to integrate different series, we have the integration test for convergence of series, and we have the alternating test that we just looked at in 9.5. So ratio and root tests are sort of unique, and just like in the previous sections, we're not going to, specifically, calculate limits. These are going to talk about convergence. They're going to use some limits. They're going to use things like that. So they're going to use limits of the underlying, of parts of the underlying sequence and all that kind of good stuff. Now, the good news is that these two tests exist. The bad news is that, like I said earlier, there's sort of a three prongs on the outcomes that we could achieve. Now, the outcomes that we could achieve on these on these two tests, well, the outcome is either going to show that the series converges absolutely or diverges, or, and here's the tricky part, there's a third prong which is unknown. Okay? So we're going to have three options. We're going to have an absolute convergence option, we're going to have a divergence option, and then we're going to have basically unknown means, hey, this test doesn't work for this series. So let's take a look at the ratio test, and then I'll show you a couple of examples and then kind of get at what the ratio test is attempting to do. So let's say we have an infinite series, an infinite sum of this sequence A sub n. This infinite series is going to, by the way, I left off the n equals 1 to infinity because obviously we can do n equals anything to infinity if we wanted to. But this series is going to converge absolutely if the limit of the ratio between term n plus 1 and term n in terms of absolute value is less than 1. This series is going to diverge if that limit, again, the limit of the ratio of the n plus 1 term over the nth term, if that's greater than 1, then the series diverges. So we look at this special ratio, and if it's less than 1, then we know it converges absolutely. If it's greater than 1, we know it diverges. And it turns out the inconclusive situation happens when the limit of that ratio is exactly 1. So when it's less than 1, we converge absolutely. When it's greater than 1, it diverges. When it's equal to 1, this test really doesn't work. That's what it's saying there in that third option. So let's take a look at this example. We're going to determine the convergence of this series using the ratio test. So here's what we do. Now, if we were going to officially use the ratio test, what we would do is we would take the n plus 1 term over the n term and then take the limit as n goes to infinity. So here's what we would do. We would take this underlying sequence, n factorial over 3 to the nth power, and we take the n plus 1 term. Now, if you plug in n plus 1, you get n plus 1 factorial in the numerator. And if you plug in n plus 1 in the denominator, you get 3 to the nth plus 1 power. In the denominator, or I should say, the nth term is just going to be n factorial over 3 to the n. Now, we can algebraically manipulate that. If you do, let me actually go ahead and do this. The easy way to do this is to say, well, this numerator, let's take and multiply that times the reciprocal of the denominator. So multiply times 3 to the nth power on top, and then n factorial on bottom. And then we get some canceling out that happens. All right, so, whoops. Some canceling out is going to happen. Let me explain this using, I'll try to explain this using what we have here. So first off, let's multiply this together. 3 to the n, I'm going to place in front. Whoops, undo that. So we're going to go 3 to the nth power, and then I'm going to put times n plus 1 factorial. In the bottom, 3 to the n plus 1 times n factorial. All right, let me put a times symbol there just so we can see that. Now here's the deal. 3 to the n plus 1 is just 3 to the n times another 3. That plus 1, n plus 1, that just means, again, if you have 7 as your n, you get an 8 as your exponent. So you're taking 3 to the nth power times another extra 3. And obviously 3 to the nth and 3 to the nth will cancel each other out. So now we can erase those. And we're just left with n plus 1 factorial over n factorial. Now, n plus 1 factorial, that can actually be expanded out. N plus 1 times the next lowest positive integer, which is going to be n, times the next lowest positive integer, which is going to be n minus 1, times the next lowest positive integer, which is n minus 2, all the way down till you get times 2 times 3, times 1, times 3, times 2, times 1, etc., etc., etc. But if you really focus on this, n times n minus 1 times n minus 2 all the way down till you get to 1, that's actually just n factorial. So n plus 1 factorial is n plus 1 times an n factorial. So now we can cancel out an n factorial from both the top and the bottom. And what we get is n plus 1 divided by 3. Whoops. Hate that when that does that. There, that's better. N plus 1 over 3. And as n goes to infinity, you can clearly see the top is growing, but the bottom is staying the same. So this thing is going to infinity. Now, this thing went out towards infinity. If you recall back on the ratio test, limit is greater than 1, therefore this sum diverges. By the way, I didn't mention this earlier, but I left off the absolute value signs when I was doing this because all of these terms are positive anyways. So absolute value is not going to do anything. So therefore, this infinite series diverges. Okay, again, that limit of that ratio is bigger than 1. Infinity is, again, much, much bigger than 1. So there you go. Now, I want to point out what the ratio test is actually accomplishing. And once we see what the ratio test is actually accomplishing, we can skip the calculations and we can go right to the end result. So let me take a look at this infinite series once again. And I claim that I should have already known that this diverges because of this underlying sequence n factorial over 3 to the n. If I take a look at that underlying sequence, all I have to do is realize we have a factorial growth on the top, but a geometric series type growth on the bottom. So we have factorial on the top versus a geometric, or you can think of that as also exponential, on the bottom. So whatever you'd rather write, factorial or exponential. And it turns out that factorial is a faster growth than exponential. And therefore, this factorial will dominate. I say dominate. What that means is as n gets really, really big, this top growth is going to be growing so fast that it's going to make the bottom growth look like it's standing still. So the factorial is a faster order of growth. It's a different type of growth. So because factorial growth is a faster order of growth than exponential, the top is going to, again, I'm going to say dominate, meaning it's going to take over. It's going to be the faster growth. And because the top is a faster growth, we have a fraction which is never going to 0. So therefore, this diverges. And that's what the ratio test is really good at. It's really good at saying, oh, we have a fraction and we have different types of growth. We have exponential versus factorial. Which one of those is going to be dominant? Which one of those, as n gets bigger and bigger, is going to sort of take over the fraction? And in this case, factorial takes over the fraction, and so since the factorial is on top, the whole series diverges. All right? So that's really what you should think of when you're dealing with the ratio test. Without having to calculate all these limits, ask yourself, well, which piece is the faster growth? Factorial or exponential or n to a power, and all that kind of good stuff. So now it's a good time, by the way, to remind you that faster growth versus that slower growth faster growth versus slower growth thing that we did earlier. Faster growth stuff that we looked at was things like n factorial. Oops, I don't want to do that. That was one of the fastest types of growth that we've seen. The exponential, b to the power n, where, let me go, b to the nth power, where b is greater than 1. Maybe we should put r there so that it matches our exponential geometric formula, r to the n, where r is greater than 1. That's a really fast growth. Into a power type growth we looked at. Again, the geometric overtakes the n to a power, but the factorial is faster than that. And then that power can be anything. That power could be 8, it could be 5, it could be 1, it could be 0.1, whatever it is. But as long as that power is positive, then we do have growth. Maybe I should signify that as well. P greater than 0. If P is less than 0, then we have decay. And then at the very slowest type of growth, like anything with a natural log or some log base, some log of some other base, would be a really slow growth. So factorial is faster than geometric. Geometric is faster than n to a power. Natural log is slower than everything. So using that sort of understanding of what the ratio test is, by the way, this is what I just wrote down, right? Faster factorial, then b to the n, then n to the p, then natural log. So using that understanding of which thing is faster and which things are slower, I want you to go ahead and try to do example 2 without calculating the limit of the ratio. Use the ratio test in the informal way that I'm talking about, in that saying which one of those pieces is a faster growth. Go ahead, push pause on the video, and do that. All right, so here we go. So we have n squared over 5 to the n. Now n squared is a power of n. 5 to the n is geometric. Geometric is going to have the faster growth. Again, we do have to make sure our base is bigger than 1 in terms of absolute value if we want to dominate there. But the geometric is going to take over, and that is the faster growth. Since it's in the denominator, the series has to converge. All right? The denominator is going to go really, really big, so the limit of this thing, eventually goes to 0. And because we're at a very different types of functions, we know that this thing has to converge. All right, so this thing has to converge based on the ratio test. And by the way, not only does this series converge, but it actually converges absolutely because of the ratio test. The ratio test says diverges, converges absolutely, or the unknown. I want you to think through this example now. We haven't dealt with n to the nth power before, So it doesn't actually exist yet on our faster growth to slower growth chart, but I want you to take a second, push pause on the video, and compare n factorial to n to the nth, and decide which one of those things is going to be a faster growth based on, and based on that, then determine using the ratio test whether this infinite series converges absolutely or diverges. Here's our series, sum of n factorial over n to the nth power. Obviously, we've dealt with factorial before. This n to the nth power is unique in that we haven't really dealt with it before, so we don't know where it falls on our list. So whenever that happens, just kind of draw a table and use some logic to figure out which one of these is the faster growth. Now, you'll see very quickly that in factorial, if I plug in 1, you just get 1. N to the nth, if I plug in 1, you just get 1 to the first power. Okay? Let me make all these things. There we go. If you plug in 2, you get, 1 times 2. If you plug in 2 to n to the nth power, you get 2 times 2. If you plug in 3 to n factorial, you get 1 times 2 times 3. If you plug in 3 to n to the nth, you end up with 3 times 3 times 3. Go 4, 1 times 2 times 3 times 4, whereas n to the nth power, n to factorial is 1 times 2 times 3 times 4. N to the nth power is 4 times 4. Excuse me, times 4 times 4. That first, I typed in the dollar symbol. And this pattern keeps going on. Now, hopefully you can see that on the left-hand side, with the n factorial, we're always multiplying by the next highest number. On the n to the nth power, we're not only are we multiplying by that next highest number, but then we're also increasing all of these previous numbers by 1. So hopefully you can see that the right-hand side is always going to be more than the left-hand side. And moreover, the n to the nth power, as we get bigger and bigger and bigger numbers, these discrepancies are going to be bigger and bigger and bigger, right? So here, we took, 1 times 2. The difference was a factor of a multiple of 2. Here, the difference of just the first term, the first thing we multiply, is a difference of a factor of 3. Again, first thing you multiply is a difference of a factor of 4. Difference of a factor of 5. Again, that's just the first piece you multiply. That doesn't even count the middle pieces being greater as well. So what we're saying here, or at least what I'm saying, is that the n to the nth power is a faster growth even than n factorial. It is in the denominator. So the series converges absolutely. All right. So this series converges absolutely. And there you go. n to the nth power is faster growth. So if you wanted to, you could scroll up. You could put faster growth n to the nth power, n to the nth power, even further left on the scale than n factorial. That's not one that comes up a whole lot, but it is an interesting case. Now, another thing that is kind of troublesome about this ratio test is that it actually doesn't work when both the numerator and the denominator are both into the p-type functions. When both the numerator and denominator are into the p-type functions, then actually what we end up with is this inconclusive scenario. You take the limit of n plus 1 term over the nth term, and it turns out it'll give you a 1. So with with a infinite series whose underlying sequence is n to the p over n to the p, we have to use another test rather than the ratio test to determine this. Now the good news is we already know, limit comparison tests. If you were to do this infinite series, you wouldn't use a ratio test, you'd use a limit comparison. You saw this n squared over n to the third, you'd say, oh, n squared over n to the third, that's going to behave just like 1 over n is. We know the infinite sum of 1 over n diverges because of the p-series tests. Therefore, this as a limit comparison also diverges. All right. So whenever you have n to a power over n to a power, again, ratio test doesn't work. You can't just say the bottom grows faster, because even though it grows faster, it's not on a different scale. Hopefully, it's not on a different order. In other words, what I mean by that is when I say faster growth versus slower growth, if two things both fall in the same category of n to the p, that's not slower growth in terms of the ratio test. The ratio test, they have to be very different types of functions that we're comparing, like factorials versus geometric, or n to the nth versus factorials, or geometric versus n to the p. All right, so hopefully that makes sense. Ratio test says which is bigger, but the ratio test considers all functions that are n to the some power on the same level. So you can't just say denominator grows faster. It does grow faster, but it grows on the same level as the top. And in this case, we would have to use the limit comparison test. You'd say compare it to this thing diverges, therefore my original series diverges. Now the other test in this section is called the root test for an infinite series. So the root tests, instead of doing a limit of a ratio, it does the limit of a root. So it takes the limit of the nth root of the absolute value of the nth term in the underlying sequence. And if that limit is less than 1, then this sum is going to converge absolutely. If this limit is greater than 1, this sum is going to diverge. And we get an inconclusive situation if this sum is equal to 1. Now, we're going to do this by hand once, and then I'll show you what it's actually trying to accomplish. So let's take a look at example 4. Example 4 says take the infinite series n plus 8 over 7n minus 3 all to the power n. So we have this sort of term raised to an nth power. This is actually what the root test is really good at dealing with. So let's calculate the root test. So here it is. This infinite series, apply the root test. Now the root test says take n plus 8 over 7n minus 3 all to the nth power. Take the limit as n goes to infinity of the nth root of the nth power. Now the nice thing about this, and the reason why this is a good test when we have nth powers here, is because the nth root of the nth power will cancel out, and you'll end up with limit of n plus 8 divided by 7n minus 3. As n goes to infinity, well, n over n, we just take off the coefficients. That becomes a 1/7. Obviously, 1/7 is less than 1. So what we know about this is that this infinite series has to converge absolutely. There you go. So series has to converge absolutely because of that. Now, by the way, what this root test is actually accomplishing, it's actually saying, well, we have a series here which kind of looks in some ways geometric. We're taking this thing, even though it's not a base, which is always the same number, not base 5 or base 1/5 or base 1/2 or anything like that. So even though our base is changing, it kind of looks geometric. And what's our base doing? Well, our base is, after n gets pretty big, is acting just like 1/7. 1/7 is less than 1. And so what it's kind of doing is it's kind of saying that we have something that's like a geometric series here. We have something that looks like a times r to the n. And in the geometric series, we knew that the series converged when the number r was less than 1 in absolute value. And so if we have something that's not a single number there, if r is some sort of a rational function, speaking to r's are this rational function here. Let me try to highlight that. That rational function, we really need to know what it behaves like when n is pretty big. And this behaves like 1/7 when n is big. And so this might as well have been very much like a geometric series where r was 1/7. And so that's what the root test is good at. It's good at looking at something weird raised to an nth power and saying, well, what does that something weird behave like? If it behaves like something that's less than 1, then this is like the geometric series where r is less than 1, so we converge absolutely. If that r happened to be bigger than 1, we knew the series would diverge. And if the r was getting close to 1, then the root test would be inconclusive. So what I'd like you to do is understanding comparing the root test to geometric series. I want you to take a look at this example and use the root test to determine if this is going to converge absolutely, diverge, or be an unknown origin situation, or unknown convergence situation. That's a better way to put it. Push pause on the video and do that. Our series again has raised to an nth exponent. That means we say it's like a geometric series where the r is equal to 2 to the n to the third plus 5 over n to the third plus 2n plus 5. Now when r gets big, that's going to be essentially like r equals 2. All right? So basically, we might as well have had 2 to the nth power in this situation. And we know that if r is bigger than 1, namely here, r is equal to 2, then this thing has to diverge. And that's it. So that's what the root test is actually really good at accomplishing. I want you to do one more example using the root test. Go ahead and push pause on the video and try this one. All right, so in this case, our underlying base that's being raised to the nth power is 6n plus 8 over 6n minus 3. If I look at that, that's like 6 over 6, which is like a 1. And so take the limit as n goes to infinity, you get 1. So what we're saying here is this is like taking a 1 to the nth power. And 1 is the unknown situation. So in this case, the root test gives us an unknown answer with the root test. All right. You'd have to turn to some other knowledge about this. By the way, this one, it turns out, does diverge, but that's using different tests. So there you go. So root test is unknown for a situation like this. Now, lastly on this stuff, I want to say a lot of these tests that we're using, whether they're the root tests or the ratio tests or, well, any other test that we've been doing, there's a number of different tests that you can use with some series. Some series you can use multiple tests with. This is an example. It turns out this infinite series, you can use either a ratio test or a root test and get the same answer. Okay. Now, the root test is going to be a little bit trickier. I'll show you the root test first because the root test, like I said, is really good with stuff that you've raised to the nth power. This has a component that I haven't raised to the nth power, so the root test is a little bit more difficult there. But the ratio test would probably be a little bit easier. So you could do this with the root test. In fact, let me not do that because I think it's probably not worth our time at this stage. But it turns out the root test does work for this. However, the ratio test is easier in this situation. Using the ratio test, we'd say, well, we have n over 4 to the n as the underlying sequence. When you take the series, when you add up all the terms, we're dealing with n to the p growth on top versus geometric growth on bottom. Geometric growth is a faster growth, again, as long as the base is bigger than 1, which it is. So geometric grows faster and is in the denominator, so the series has to converge absolutely. So based on the ratio test, this is converging Absolutely. There we go. And that's it. Now you can see sort of some of the difficulties with these situations. The hard part of putting all of the stuff that we've dealt with from 9.2 up to right here, 9.6, is determining which test to use, right? We've dealt with so many different tests. We've dealt with comparison tests. We've dealt with the integration tests, P-series tests, alternating series tests, and now the ratio and root tests. There is a list of these tests in the book at the end of section 9.6. That table will be on the, or a part of, I should say, the formula sheet for the Chapter 9 test. Okay, so this table has, nth term is equal to this. So it has all of the different summary of tests for the series. What I've clicked on here is in our Moodle shell, the practice test 3. If you click on the formula sheet, the PDF version of the formula sheet, the second page will give you the summary of tests. So you can see a geometric series. It lists out what the series should look like. And then the condition for convergence says if the absolute value of r is between 0 and 1. I've been saying if r is between -1 and 1. Divergence when absolute value of r is greater than or equal to 1. And then sometimes the comment will tell you, well, again, this one starts at 0. Be careful of that. Well, the sum of the geometric series is a over 1 minus r when it converges. Telescoping series here, we've dealt with those. The P-series test converges when P is bigger than 1, diverges when P is less than 1, or less than or equal to 1. Alternating series, we know an alternating series looks like this. It has this -1 to the n minus 1 with the positive parts. And condition of convergence is that we're decreasing and the terms go to 0. There's this remainder piece too that we dealt with last time. Integral says if the integral of f of x converges, then the series converges. If the integral of f of x diverges, series diverges. There's also a remainder test there, but we didn't go over that. The root test and the ratio test, or what we just went over, converge when ratio or that weird root is less than 1, diverge inconclusive when we get equal to 1. And then the direct comparison and limit comparison tests as well. So you can see that sheet in the PDF formula sheet for Chapter 9 that's posted up on Moodle. All right. So that is something that you will have to look at. Now again, you'll have these things to look at, but I do want to be very clear that I'm not going to ask you to compute the limit. I'm not going to ask you to compute this limit by hand or this limit by hand. I want you to understand what the ratio and the root tests are doing, what the comparison tests are actually doing. The ratio test is comparing different types of growth. Again, end of the P and the end of the P are the same type of growth, but end of the P and geometric are different types of growth. And the geometric is going to take over, is going to dominate. It's in the denominator, so the whole thing's got to go to 0 pretty quick. Ratio test is that. Root test is, well, how does this compare to r to the nth power? How does this compare to a geometric series? If r is like 1, then we're going to get an unknown situation. If r is bigger than 1, is like something that's bigger than 1, then we're going to diverge. If r is like something that's less than 1, then we're going to converge absolutely. All right. So those are the types of things that I want you to understand. I want you to understand what's actually going on. All right. So that is it for section 9.6.